Thank you. I'm very happy to be here today. I'm going to talk to you about a new model that we have built, and it concerns the prediction of solar energetic particle events. So the name is the probabilistic solar particle event forecasting model, or for short, PROSPER. And this is a collaborative work of the National Observatory of Athens, of the University of Turku, the University of Barcelona, and the European Space Agency. So a little bit of background and motivation. What we know is that when we have strong solar eruptive events like solar flares and coronal mass ejections, it may be the case that we have the acceleration and release of particles, which we call solar energetic particles, which are then routed through the interplanetary magnetic field down to Earth. We have an armada of different missions that are monitoring the sun. Other missions, as we have seen in the previous talk by Olga, like Solar Orbiter and Parker Solar Probe, are monitoring the sun in a closer radial distance, whereas we also have watchdogs at L1 like SOHO and ACE. Basically, when we see SCP events, we see enhancements above the background level of the detector, and the shape of the SCP event varies with respect to the position of the observer with respect to the source of the particles. Now, in these kinds of studies, there are basically two scientific questions that one needs to address. So the first question is that if we have specific parameters of solar eruptive events, can we identify the probability that an SCP event will actually take place? And the second question is if we can predict the characteristics of the SCP event, like, for example, the peak flux, the fluence, and the duration, based on the characteristics of the parent flare and the parent coronal mass ejection. Now, also some info about the probabilities. We have the independent probabilities. So if this is our space, the probability PB and PA are the independent probabilities, the probabilities to observe A and B independent of each other. We also have the conditional probabilities, which is the probability to observe A under the condition that B is true and vice versa, the probability to observe B under the condition that A is true. And we also have the joint probability, and this is the joint probability here of observing A and B together. So what Bayes actually showed is that it is possible to calculate the probability, the conditional probability to calculate B when A is true. And this is equal to the inverse conditional probability, thus the probability to observe A when B is true, multiplied by the independent probability to observe B and divided by the independent probability to observe A. Basically, the take-home message here is that through the Bayes theorem, it is possible to calculate a conditional probability when the joint probability is really difficult to calculate. So this is exactly what we did in the PROSPER model. We applied the Bayes theorem, and this is how we translated, let's say, the Bayes theorem to our particular problem. So we want to identify the probability to get an SCP event, when an event, and here with an event, we mean when a CME, when a flare, or when a combination of a solar flare and a CME has taken place. So that said, it means that the PROSPER comes in three flavors. We have one module when we only use a CME input, another module when we have only solar flare input, and another module when we have combined information of solar flares and CMEs. So I'm going to walk you through the details for the first case for the CME input, and then I'm going to show you the results for solar flares and CME input. So the first thing for the CMEs, what we did is that we have our data, and we bind our data with respect to their width. So we have CMEs that are characterized as halo, CMEs that are characterized as partial halo, and CMEs that are characterized as non-halo. And what I give you here on the right-hand side is the CDF, the cumulative distribution probability for those CMEs. So with blue points here, you can see the halo CMEs. With the red points here, you can see the partial halo CMEs. And with the green points here, you can see the non-halo CMEs. And the x-axis, of course, is the speed of the CME. In order to apply the Bayes theorem, basically we need three things. So in order to infer the probability to get an SCP event when you know the speed of the CME, you need two distributions. One is the distribution of all CMEs in your sample. The second is the conditional distribution of the CMEs when you know that these CMEs are associated to an SCP event. And the third thing is a factor. So what is the probability for that specific binning to get an SCP event? So it's a factor from a database. So what I give you here is the actual fitting that we employed for the HelAS CME case. So in the left-hand side, you can see the CDFs for all HelAS CMEs in our sample. So here in the x-axis, you have the speed of the CME. The black points corresponds to actual data. So these are points. And the red line here corresponds to our fit. And here you can see that we upload the log normal fit, what is the mean absolute error, and what is the fraction of the data that are being explained by this fit. And on the right-hand side, you can see a similar plot, but in this case, we have the distribution for under the condition that these HelAS CMEs are associated to SCP events at this specific energy. And again, the fit is the red line here. Then once we have accomplished this, we applied this to all different integral energies of interest. So 10 MeV, 30 MeV, 60 MeV, and 100 MeV. And this is the overall view. So here you can see the CDFs for all HelAS CMEs. For all HelAS CMEs is with the black color here. And for HelAS CMEs that are associated to SCP events at different energies, these are color coded with different colors here. So from 10 MeV up to 100 MeV in yellow color. So then in order to go from the CDFs to the PDFs, we took the derivatives. And of course, since we have log normal fits, we end up with Gaussians. So this is what we got for all HelAS CMEs in our sample and for the HelAS CMEs that are associated to different SCPs at different integral energies of interest. And finally, when we applied the Bayes approach, this is the result. So basically, each line here corresponds to its different integral energy of interest. We're talking about HelAS CMEs. So if you know the width and you know that this is a HelAS CME and you know the speed of the CME, then you can derive the probability to get an SCP event from the y-axis here. Of course, we did that for all different widths. So HelO, partial HelO, and non-HelO. HelO is here with the blue color, partial HelO with the red color, and non-HelO with the green color. And for its integral energy of interest, as you can see, these different panels. So basically, this y-axis here provide the probability to get an SCP event when you know the characteristics, when your input is the width and the speed of the driving CME. Then we used as input solar flares. So what I give you here is the actual data that we have in our database. So on the left-hand side with red, you can see all solar flares of our sample. And in the right-hand side, you can see with black dots, the SCP, the solar flares that are associated to SCP events. Here we impose a bin on the binning on the width. So everything that it is above a longitude of greater or equal to 20 degrees, we consider as well connected. So all these guys here, and everything that it is on the left-hand side here is considered as poorly connected. And when we apply this Bayes theorem, this is what we got. Again, each plot corresponds to its integral energy of interest. And what you can see here is that if you know the longitude of the flare, then you can select which line to use. For example, here the blue line is the well-connected and the red line is the poorly connected. And if you know the flare flux, so the magnitude of the flare, you can directly come here and derive the probability to get an SCP event. In the third flavor of Prosper, we use the combination of all aforementioned selections. So we have 3 selections for the CME widths, HelO, partial HelO, non-HelO. We have 2 selections for the longitude of the flare, well-connected and poorly connected. And we actually have 5 different integral energies of interest. So we did all these combinations. And I give you here one example. So this refers to HelAS CMEs and well-connected flares. This output here provides the probability to get an SCP event when you know the speed of the CME and the magnitude of the flare. Each line here corresponds to a class of flares. So C1, M1, X1 is the red one, and X10 is the magenta one. And down here you have the speed of the CME. So if you are dealing with an M1 class flare, for example, and you know the speed of the CME, you can again directly from the y-axis here derive the probability to get an SAP event. And on your right-hand side here, it's just a parametric space. So it's a contour plot, and here you have the speed of the CME, and here the flare flux, and overlay you have the probability to get an SAP event for that particular selection. Now, once we have identified the probability to get an SAP event, the second question to address is if we can derive the peak flux, the expected peak flux of the SAP event. So in this case, again, we have three sub-modules, but this is more plain. So the first thing is that we try to see what is the energy that we predict that these particles will reach. So in the case that we predict that these particles will reach to an integral energy of 100 MeV, then we bin the data, we filter the data accordingly, and we get CDFs bins like that. So the red line here is for the 10 MeV, the green line here for the 30 MeV, and the blue line here for the 100 MeV. And what we are actually providing is the output for the 50% confidence level. So this is the lower limit of our prediction down here, these values here. And here is the 90% confidence level. So here is the upper limit of our prediction in the CME case, that is. We have done the same thing for the solar flare case. So again, what I give you here is the same thing. We predict that we are going to see particles up to 100 MeV, and we bin the data accordingly. So in the flare case, we're providing these values here, the 90% confidence level as the upper limit, and the 50% confidence level as the lower limit. And this is what we have in the case of solar flare and coronal mass ejection input. So when we are using a combined input. Now, in terms of validation, Prosper took part in the SIGN SAP model validation challenge. So we were given these 10 events from the NASA CCMC and SRAG. You can see here the peak fluxes at 10 MeV and 100 MeV, and the characteristics of the parent flare and the parent CME for each of these events. So what I give you here is actually the outputs, the probability to get an SAP event. And in the x-axis, we have the actual dates of the SAP events. The histograms here corresponds to the achieved probability to get an SAP event. This column here corresponds to the flare module. The column in the middle corresponds to the CME module. And the column on the right-hand side corresponds to the combined flare and CME module. And what I would like to draw your attention to is that here we have a flat line. This is 0.28. This is the probabilistic threshold above which we interpret all the probabilities that we derived as a yes or no probability. So everything above this line, we say that this is an SAP yes. So basically there is one guy here, the 14th of July, which we didn't predict as an SAP yes. We have almost 20% probability of SAP occurrence, but it is less than our probabilistic threshold. However, when we use the CME module, you can see that we have, so CME information alone, you can see that we double the probability to get an SAP event. And of course, when we use the combined information of flare and CME, we have we achieve very high probabilities of SAP occurrence in all different SAP events. And finally, this is the validation with respect to the peak flux. The blue points correspond to the 50% confidence level, and the red points correspond to the 90% confidence level. The plots above correspond to the 10 MeV and down here to the 100 MeV, and each column corresponds to different sub-modules. You can see that, for example, in the case of the 10 MeV, the 50% confidence level is very close to the dichotomous line here, which means pretty good prediction. We have a large scatter here in the 100 MeV of almost 1 order of magnitude. When we shift to the CME module, we have higher estimations, higher forecasted peak fluxes in the 10 MeV, but we have a better result here in 100 MeV. And when we shift to flare and CME inputs, the 100 MeV seem to provide very good results. Now, the take-home message is that the Prosper model is integrated into the ASPECS tool, the Advanced Solar Particle Event Casting System, which is freely accessible through this URL here. And that was all from me. Thank you very much for your attention.
Thank you very much, Thanasi. Very nice tool. Do we have any questions? Please raise your hands or just unmute yourself. And yeah, Spiro, please go ahead.
Yes, thank you very much, Thanasi, for the very nice presentation. So I wanted to ask you about when the tool is working online, in real time. How do you get information concerning the CME properties, whether your CME is hollow, partial hollow, etc.?
So,
do you use Cactus?
Yes, unfortunately, as you know better than myself, we are using Cactus because this is, let's say, an online available solution. The problem with the CME information when it comes to forecasting or nowcasting of SAP events has to do also with the telemetry. That's the first thing, because we have data available and identifications of CME available every 6 hours, which means that the CME module is a module that we can use only when this information is available. And of course, the misidentifications or the multiple identifications of the same CME by Cactus is also a second problem in the tool.
Okay, thank you.
Thank you.